Hello. Right, I'm back. Let's wrap this up with some soft examples, right? Okay. So you can refer to the question in your module, yeah? It's example 2.6 A on page 52. 2.6 has got the A, B, C, D, so we'll go to each and every one of them. I hope that will make you happy. Alright, let's look at the question. It says, is the infinite slope in the figure stable? If not, how much above the rock surface will the slip occur? Already the question is suggesting to us that it's not safe. If it's safe, that's not even the question, right? So let's look at it, how to resolve it. Look at the diagram carefully. There's a rock surface at the base, infinite slope. So layer A, layer B, and the height is 4 meters, 6 meters, inclination at 20 degrees. As usual, extract all the information given, blah blah blah, as we discussed just now. Now, first step. For the first layer, that is layer A, we need to identify whether the failure is going to take place in layer A or layer B first. So that's the first step, okay? So what do? There's only one equation to be used, this one. ZA, that is the depth or the height where the failure plane could take place, equals to C, that's the cohesion, the strength, over gamma T cosinus I sinus I. Simple as that. Come on, if such an equation is required, do you think it should be given, or you think that you should know? Alright, so once you know that, all you need to do is to pop in the numbers and you get the answer. So I've written down here for you as well. Sinus 20 is 0.342 and cosinus 20 is 0.9397, and you get the answer of 4.91. Alright, and 4.91 is greater than 4 meters. Layer A, if you recall, is only 4 meters thick. So if it's 4.91, you know it's getting into layer B. So this is where the fun begins. Okay, so you say that it cannot happen. It can't happen in layer A, hence it has to be in layer B. But where about in layer B? Let's check it out. So now we move on to layer B. Similarly, we are going to find out what is the driving force that is exerted by A on B, because we know that is A on its own is not going to be stable, but it's going to add on to the driving force into layer B, right? So now we are going to determine the driving stress. So again, it's the same formula. Look at it. It's actually moving the bottom bit to this side. Can you see? Because tau, I tell you, the shear stress is actually the shear strength. It's the same. So you move it over algebra, it's actually the same equation. Can you see? So now tau A or C is gamma Z cosinus I sinus I. Put it in and you get the answer 24.4 kilonewton per meter square. So this value is the driving force caused by layer A onto layer B. So in other words, now your layer B, which initially has a shear strength of 50, is not 50 anymore, because it needs to use up some of the 50 kPa to resist this 24.4. So what is the remaining shear strength that layer B has to take care of itself? Yeah, right? You just minus it off. So the remaining strength in layer B will be 50. That is the shear strength of layer B minus of the driving force coming down from layer A. So you get 25.6. Good? Follow? Good. Now, the last bit. Where is it going to happen now? I know it's going to happen in layer B, the failure plane, but where about? Again, the same formula. What do we do now? You have to use the C left, whatever you found here, the remaining shear strength that is in layer B, divided by again gamma, cosinus, and sinus. You get 3.98, so let's say about 4 meters. Alright, remember, the formula goes that in such a way that the Z, the distance or the height that we obtain, is actually measured from the top of that layer that you're talking about. So in this case, because you're talking about layer B, so it's 4 meters from the top of layer B. If you recall, layer B is 6 meters high, right? So in other words, it's actually 2 meters above the rock surface. Am I right? Okay, so that's where it's going to happen. Just pause a moment and we review what is actually happening here. The slope was 4 meters layer A and then 6 meters layer B. But the failure plane is going to be 2 meters above the rock surface, meaning that 8 meters thick of soil, layer A plus layer B, is coming down. Alright, with this kind of driving force around. You can imagine the massive destruction that will actually cause. Okay, good. Now let's look at 2.6 B. Again, infinite mass, infinite slope again tells you that gamma T, remember, gamma is a unit of soil. If the question doesn't tell you whether it's T or B or whatsoever, assume that it's gamma T is gamma total, and gamma total is also known as gamma bulk. Right? Gamma B is bulk unit weight. If this gamma is assumed as gamma B or gamma T, right? It's 20 kilonewton per meter cube, and it's just stable at the gradient of 30 degrees. Question 1. If we inundate the soil mass, meaning it's flooded, alright, water table is right to the top, it's wet, will it be stable? If not, what is the inclination that you need so that the slope remains stable when water is filling up the whole slope? Okay, and the second question is about water flowing through. So by looking at the question, we know that definitely there are two answers here. Alright, definitely there are two answers. If water flow and water being static, the first case is the water being static, the second case being is flowing, are going to produce the same result, they wouldn't be asking you. Alright, and now it should click in your head that we saw earlier on the explanation about infinite slope. When there is water coming in, remember the flow nets, the flow lines, and then your equipotential lines, the squares, and you consider one element. Yeah, you're right. The pore water pressure needs to be taken into consideration, and it's actually good or bad for slope stability. Again, you remember correctly, it is bad. Alright, now let's look at how the calculation goes. For the for the condition of failure for the submerged slope, right? Submerged, remember, water inundating it, so it's static water, flooded. So it's the same as if it's a dry slope. Why? Because it's a sandy slope. So in sand, it's fast draining. Water goes in, water comes out quickly, almost immediately. So whether it's wet or dry, it's going to be considered the same. Alright? Hence, what is the answer? The slope will remain just stable at an inclination of 30 degrees. See? Just stable, because the question says it's just stable. If you bring the gradient up to 31, 32 degrees, the slope will start to destabilize, will start to move. That is what is meant by just stable. Alright? And it is also telling us just stable meaning the soil is at the maximum of its shear strength. Alright? Maximum of the shear strength. In other words, is the minimum. Is the minimum that is required for it not to move. Alright? Anything more than that is going to start moving and be destabilized. Now let's look at the second bit of the question. Now it's water seepage coming in. Alright, so this is the equation. You recall the tangent of your eye, that's the gradient of the slope, must be a portion of your tangent phi. Alright, phi, remember, is the friction angle of soil and the sand. So of course, it's only phi, there's no cohesion, no C. Gamma T minus gamma W. Alright, simple as that. Now, in this example, the gamma W is being used as 10, but you know that to be precise, it's 9.81. Though in the exam, we are running out of time, or what, just put 10 is alright, okay? And blah blah blah, you just calculate. How can we make a mistake? Maybe we forgot how to press the calculator to get out tangent. Just practice here. Make sure you get these answers, and you find that the angle I, that is the inclination of the slope that is permissible, is actually 16.1. Okay, and the slope is actually at 30. Okay, meaning what? If the slope is not safe, alright, because it's just stable at 30. Now, 30 is safe. Alright, this is the slope. 30 is safe. Now I'm telling you that it is for the situation where you have water seepage coming through, it is only safe. It is 16. 16 is more gentle. It's a gentler slope, right? This is 30. This is 16. This angle we are talking about. Okay, so in other words, it's going to fail. Anything more than 16 is going to fail, right? So the answer is it's not safe. Got it? Good. Now, question C. Now we are going to use Taylor's stability number. Again, it tells you that you're supposed to find the safety factor. Finite slope is clay. Now it's clay, is no longer a sand, so there's a CU or SU, depending on which book you're looking at. It's 40 kN per meter square, gamma 20, slope angle 30, and two surfaces, one the ground surface, and then we have the rock surface. Okay, extract the information as such, and look at the diagram. Okay, here's the diagram. Base of the slope, top of the slope, this is H. What is H? It's 10 meters, right? It's given there. And to the rock is 20 meters. So this is 20 meters. Okay? So if I know H is 10, DH is 20, so I know D is 2. I need to know D. Otherwise, I can't read off the Taylor's chart. Alright? So now let's look at Taylor's chart. Right. Again, remember, we have the angle of the slope given was 30 degrees, correct? So we look at this row, and our D is 2. So read off NS is 0.172. Now you pop it back into your equation. Alright, that's the equation there. So what is the minimum strength that you require? It is actually gamma, H, and S. So gamma is 20, H is 10. This is H, remember? And NS, you just found it, 0.172. This is the answer you get. Okay, but that is not the final answer. The question is, what is the safety factor? So the safety factor is simply what you have to resist the failure against what divided by the driving force. All right, what you have over the driving force. Then you know how many times. All right, how many in what multiple is your soil mass, is your slope safe against the driving force? So it's 40. That is the existing strength that you have. All right, divided by the driving force, that is 34.4, and you find that you have 1.16, just about more than 1, so it's just about safe. All right, so that's how we interpret it. It should be more than 1 to be safe. Okay, right. Now the last question here that we have is using the method of slices. So in this case, you are not asked to slice them out. It has been sliced up for you. It has been calculated for you. All the W sinus alpha has been calculated, and W cosinus is also calculated. This is C0 phi 30. That means it's a granular soil, most likely a sand. Okay. So all you need to do is to look at the table, tabulate it. It's given to you each slice, blah blah blah, and you total them up. What is T? What is P? And remember, the equation is a summation of S over summation of T. Again, see, the safety factor is about what you have. Alright, this is a shear resistance. T is the driving force. And we know that S is actually P times tangent phi. So just put the numbers in, you get 1.4. So 1.4 is greater than the 1. So you're alright there. Okay, so that's all for 2.4. We have wrapped up the chapter 2. Any questions, as usual, you can PM, you can ask a group, you can ask among your friends or whatsoever. Okay, thank you. Stay home, stay safe. Bye-bye.